Special types of linear programming problem, graphs and networks. What is a graph? A graph is a collection of points called nodes, some of which are joined by lines called arcs, edges, or branches. An arc joining nodes I and j will be denoted by I, j. A loop is an arc of the form I, or j, j. That is, an arc joining a node to itself. If the nodes of a graph are numbered consecutively from 1 to n, the graph can be represented by a matrix called the incidence matrix, denoted by M, which is equal to Mij, where Mij is 1 if node I is connected to j, or 0 otherwise. The matrix M is equal to its transpose. From this definition, we have a graph here, and this graph has 7 points which are 7 nodes, and it has lines joining each of these nodes to other nodes. These lines are called arcs, edges, or branches. This arc can be denoted by 2, 3 or 3, 2 because there is no sense of direction in the arc. And supposing we have a line right here, this is also an arc which is joining 2 to itself. So right here, labeling this arc, we'll have 2, 2. Because this arc is joining the node 2 to itself. So likewise, we can label every other arcs that we have in this graph. Right here, we can have 2, 4 or 4, 2. Here we can have 1, 3 or 3, 1. Every graph can be represented with an incidence matrix. And how do we represent this graph with an incidence matrix? First of all, we check the number of nodes that this graph has. This graph has 7 nodes. And so the matrix that we'll have is a 7 by 7 matrix. And how do we represent it using this graph? First of all, we write out the number of nodes that we'll have in the rows, in each row and in each column. So for each column, we have 1, 2, 3, 4, 5, 6, and 7. And for the rows, we have 1, 2, 3, 4, 5, 6, and 7. We have 1 here. In this point, this place is supposed to represent the arc 1, 1, because right here we'll have 1 and we'll have 1 here. And so we check in the graph, is there any arc that can be labeled as 1, 1? And we should know that this 1, 1 should be a loop. And right here at 1, we don't have a loop. That is an arc that is joining 1 to itself. And what it means is that we will have 0 here. And so for each pair of nodes that we check, if there is an arc that connects them, we represent them as 1 in our matrix. But if there is no arc connecting them, then we represent it as 0. Right here, we don't have an arc joining 1 to itself, and so we have 0 here. Now let's check, is there any arc joining 1 to 2? Yes, there is an arc here connecting 1 and 2, and so we have 1 here. And then we check, is there an arc connecting 1 and 3? Yes, and so we have 1 here also. Is there an arc connecting 1 and 4? This arc, and so we have 1 here also. 1 and 5 is connected, so we have 1 in our matrix. Now there is no arc joining 1 and 6, and so right here we'll have 0 in our matrix. And we'll consider 1 and 7. Is there any arc joining 1 and 7? No, so we have 0 here also. And then we go to 2. Is there any arc joining 2 and 1? So from 2 to 1, there is an arc joining them, and so we have 1 here also. And then we check, is there any arc joining 2 and 2? Right here we have a loop, and this loop can be represented as 2, 2. And right here we have 1 because of this loop. So we have 1 because there is an arc joining 2 and 2. And so we check, is there an arc joining 2 and 3? Yes, right here. And so we have 1. 2 is connected to 4. So we have 1 here. This is the incidence matrix that we can use to represent this graph. If we get the transpose of this matrix, we will still have the same matrix, which means that this matrix is equal to its transpose. A path between node I and node J of a graph is an ordered set of arcs joining I and J. And this means that a path must consist of more than one arc. And so we check, if we look at node 2 and node 5, we have an arc joining 2 to 1, and we can go from 1 to 5. And so we have a path here. We can also have a path from 2 to 4. We'll go from 2 to 1 and from 1 to 4. Or we can decide to go from 2 to 1, from 1 to 5, and from 5 to 4. And so let's find a path that is between 2 and 6. So a path is a set. First of all, we have a set right here, and then we go going from 2 to 6. We have several ways. We can go from 2 to 4, from 4 to 5, and from 5 to 6, or we can go through any other way. So let's go. Let's check from 2 comma 1, and then we go from 1 to 5. We have 1 comma 5 and 5 to 6, and we have 5 comma 6. And this is one path that can lead us from 2 down to 6. Let's choose another path that will lead us from 1 down to 7. So we say a path going from 1 to 7 will be, let's pick 1 comma 5, and then from 5 to 4, 5 comma 4, and then 4 comma 7. That is this part and this. Going from 2 to 7, we have 2 comma 3, and then we decide to go from 3 to 1, 3 comma 1, and then from 1 to 4, 1 comma 4, and then from 4 to 7. So this is a path that will lead us from 2 down to 7. And so we can pick so many other paths from this graph. So let's go to a cycle. A cycle is a path joining a node to itself. So right here we know that a path must consist of more than one arc. And so we can pick a cycle at any point. Let's check. We can pick a cycle from 4. You can go from 4 to 5, 5 to 1, 1 to 2, and then from 2 down to 4. Just that we will start from 4 and then we'll also end with 4, and that is a cycle. So let's demonstrate. Let's write this out the same way that we'll write our path, because a cycle is a path. And so right here we have a cycle from 4, and so we have 4 comma 5, 5 comma 1, 1 comma 2, and then 2 comma 4. And so we have a cycle here. We can as well get a cycle from 2. We can go from 2 to 3, 3 to 1, and 1 to 2. Or we can go from 2 to 4, 4 to 1, 1 to 2, and so on. Now, a graph is said to be connected if there is a path joining any two nodes of the graph. Considering these two graphs, we find out that for this graph, any two nodes that we pick, we can find a path that will lead us through from the first node that we pick down to any other node that we pick. And so that is the reason why we say that this graph is connected. But checking this graph, we find out that there is a node that we can pick here. There are two nodes that we can pick here. We can't find a path that will lead us to that from one of the nodes to the last one. And so we check, if we decide to check from 3 to 5, there is no path that will lead us from 3 to 5. Why? Because there is no connection here. And so we say that this graph is not connected, but we call this a connected graph. An arc of a graph is called directed or oriented if there is a sense of direction, so that one node is considered the point of origin and the other node is the point of termination. The directed arc from node I to node J is denoted by I, J bar. So if we have a point, if you have a sense of direction right here in this arc, we call this arc a directed arc. Why? Because we can move, it's showing a sense of direction that we can move from 5 down to 6. And so we can label this arc here as 5, 6, but not 6, 5. Why? Because it shows a point of origin that is starting from 5 down to 6. Now, a graph in which every arc is directed is called a directed graph or an oriented graph. And so if we have every arc in our graph directed, we'll have a directed graph. We call it a directed graph. Right here, we have every arc in this graph directed. And also for any directed graph, we can as well have an incidence matrix for it. And how do we do that? Just almost the same way we did the last one. We have 6 nodes here, and so we'll have a 6 by 6 matrix. Have a 6 by 6 matrix, and then we write out the nodes on the columns and in each row. Right here we have 1, 2, 3, 4, 5, 6. And then in each row we have 1, 2, 3, 4, 5, and 6. So after numbering the rows and the column, we check for each arc. We check for each point in our matrix. So right here we are supposed to have 1, 1, and where we have this type of arc is where there is a loop. And so we go to 1, but there is no loop in 1. And so right here we will have 0. And in this place, the arc that is supposed to be represented here is 1, 2. And so right here we have this arc directed from 1 to 2. And so it can be represented by an arc. It can be represented by 1, 2. But not 2, 1. Why? Because of the sense of direction. And so right here we're supposed to have 1, 2. And so we have 1 because there is a direction, because there is an arc that is labeled 1, 2. And so right here we have 1. Now we check, is there an arc that can be labeled as 1, 3? Yes, this arc can be represented with 1, 3. And so right here we have 1 represented with 1 in our matrix. And so we check, is there any connection between 1 and 4? No, there's no connection between 1 and 4. And so right here we have 0. Is there any connection between 1 and 5? No, and so we have 0. And we check for a connection between 1 and 6. There is no arc that is directed from 1 to 6, and so we have 0 here. And then we go to 2. There is an arc connecting 1 and 2, but this arc is flowing from 1 down to 2, but not from 2 to 1. And so we have 0 here because this arc is not facing 1. And so we check, is there a loop in 2? No. And so we have 0 here. And then we check for 2, 3. Yes, there's an arc connecting 2 and 3, and this arc is flowing this way. And so we have 2, 3 here, which is 1. And then we check for 2, 4. This arc can be represented with 2, 4. And so we have 1 here. Is there any connection between 2 and 5? No. So we have 0 here, and 2 and 6 we have 0. And then we check for 3. Is there an arc joining 3 and 1? Yes, but the point of termination of this arc is 3. And so this cannot be labeled as 3, 1. And so we have 0 here. Now 3, 6, this will be 1 because this arc will be represented by 3, 6. And so we have 1 here. And then we go to 4. Is there an arc joining 1 and 4? No. Can we find 4, 2? No. So we have 0 here. 4, 3. Yes, this arc is 4, 3. And we'll have 1 here. Is there a loop? No. 4, 5. Yes, this arc is facing 5, and so we have 1 here. And then 4, 6, we have 0. 5, 1, there is no arc there. 5, 2, 0. And then 5, 3 is 0. And 5, 4 is 0. 5, 5 is 0. And 5, 6 is 1. And right here you see is all the arcs connected to it are directed towards it. And so all through the node in Cs will be labeled, will be denoted by 0, because there is no arc going away. There is no arc pointing away from it. And so right here, this is the incidence matrix that we can use to represent a directed graph. And one thing we observe here is that an incidence matrix for a directed graph will not be equal to its transpose. And then this will lead us to an idea of a network. What is a network? A network is an interconnection of several terminals by routes between certain pairs of these terminals. Each route has a capacity, and we are interested in studying the movement or flow of material along these routes. We can study pipeline networks, highway networks, electrical power distribution networks, as well as many other kinds of network. But mathematically, we define a network as a connected directed graph for which a non-negative number has been assigned to each other pair of nodes, and this number is thought of as the capacity of the directed arc joining the two nodes. The capacities represent maximum amounts that we may pass along arcs of network. A network may be represented by its capacity matrix, which is a generalization of the incidence matrix of the capacities of the arcs. And from the network, from the graph that we discussed the last time, we have I just put in some numbers right here. Before we had a connected graph and a directed graph right here. And so if there are numbers in each of these arcs, non-negative numbers, we can call this whole graph a network. And so the difference is just that in each arc, it has a capacity that can flow from any node to any node that it is connected to. So right here from 3 to 6, we have a flow here which is 1, and from 4 to 5, we have a flow here which is 2, and so on. And so for the capacity matrix right here, for the graph we have an incidence matrix, but for a network we have a capacity matrix. And we derive the capacity matrix almost the same way that we derive the incidence matrix for a graph. So right here we have a network, and so the only difference here is just that we use numbers, these numbers, to represent the places that we have 1 in this incidence matrix. And so we still have a 6 by 6 matrix right here. And we call this the capacity matrix. We number each row and each column. So let's start by numbering the columns here, and then number each row. And so we check, is there any connection between 1 and 1? There is no loop there, and so the connection here is 0. We use 0 to represent that there is no connection between 1 and 1. And then we check, is there any connection between 1 and 2? Yes. So we can label this arc as 1, 2. And so right here we don't use 1 to represent the arc. We use the capacity that is attached to this arc to represent it. And so we have 7 here, and that is what we write here, 7. And then we check, is there a connection between 1 and 3? Yes, there is a connection here because this arc can be labeled as 1, 3. And so we have 4 as the capacity here, and we write it out in this place. And so we have 4 here. Is there a connection between 1 and 4? No. And so we have 0 here, and sent into 5, 0, and 0. And then we go to 2. Is there any, 1 is 2 connected to 1? There is no arrow pointing from 2 to 1. And so we have 0 here. Is 2 connected to 2? 0. Is 2 connected to 3? Yes. So this arc is pointing from 2 to 3, and it has a capacity which is 5. So you use the capacity to represent the arc. And so right here we have from 2 to 4, and we use the capacity to represent the arc. We have 8 here. And then we check from 2 to 5, and right here we have 0, and from 2 to 6 is 0. Then going from 3 down to 1, there is no arrow pointing from 3 to 1, and so we have 0 here. 3 to 2, 0. 3 to 4, 0. 3 to 3 is 0. 3 to 4 is also 0. 3 to 5 is 0. And 3 to 6 is 1 because the capacity here is 1. So from 4 to 1 is 0. 4 to 2 is 0. 4 to 3 is 9. And then 4 to 4 is 0. And 4 to 5 is 2. And then 4 to 6 is 0. And 5 to 1 is 0. 5 to 2 is 0. 0 here. 0, 0. And then from 5 to 6, we have a capacity of 5 there. And then from 6 to 1 is 0. 0, 0, 0, 0, 0. And so we still have almost the same thing that we have here, just that we use the capacity of the arcs to represent the places that there is a connection. A flow in a network is an assignment to each ordered pair of nodes I, j in the network of a non-negative number xij that represents the amount of material moving in that directed arc. If node I is not connected to node j, then s, j, then xij is equal to 0. So by definition, a flow xij ranges from 0 to the capacity. Now, when we talk about a flow in a network, we consider the capacity in each arc. And so we see that the flow that we can pass in this arc cannot be more than 4. The material that we can pass in this arc going from 1 to 3 cannot be more than 4. And so every flow from between any arc or any part in the graph will be ranging from 0 down to the capacity that we have in that arc. I'll explain this flow more in the next video, where we'll be talking about the maximum flow in a network. But before we end this video, we'll talk about the source and the sink in a network. In many networks, we single out two types of nodes for special consideration. The node S is called a source if every arc joining S to another node is directed so that the flow is away from S. And the node T is called a sink if every arc joining T to another node is directed so that the flow is towards C. And this means that a flow is produced at a source and absorbed at a sink. So considering this network, we have that our source node is 1 because every arc that is connecting it to every other node is directed out from it. And then we have our sync node, which is sys, because every arc that is connected to it is directed towards it. And so that will be it for this video, graphs and networks. In the next video, we'll be discussing the maximal flow problem in a network. Thank you for watching the video. Hope you enjoyed it. Please like and subscribe and follow us in the next video.